is your definition, or how would you sort of encapsulate the idea of science in really kind of general terms? What does science mean?
Yeah, so science to me is the study of the universe, basically. It's a more sort of detailed definition of science would be a systematic study of the universe via observations or via experiments. So you use observations or experiments to verify your results. And one of the main characters of science is what we call the scientific method. The scientific method is what's been basically driving science since it started, and it's been proven so successful as the sort of engine that drives science and makes it produce these accurate and predictable results. And all this progress has been made due to the development of the scientific method uh, uh, for basically for the progress of science. Um, you could think of the scientific method as basically going from making observations to asking a question about an observation, um, and then you make a hypothesis, or you do research, and then you make your own hypothesis, and from your hypothesis you do studies, experiments, observations, extra observations, and then you come up with a theory, and that's the theory that you going to share it with the rest of the scientific community or with the world, basically. Um, so to me, science is this method of going from all the way from first observing to coming up with a new conclusion that basically expands the boundary of science and basically tells people about new data, new observations about what you've came up with, basically. For example, in my work, you've already mentioned electrodeposition, which actually is another way of saying it is electroplating. You might have heard of
Okay.
electroplating. It's
Hmm.
the method used for plating jewelry with gold or silver. Sometimes they use it to plate coins. Um, in our science, let's say, just to give you an idea of what we do, just so that you get an intuition of it. So in our case, we're trying to, or the hypothesis, let's say, is that you can use this method for making tiny or for plating tiny objects, not jewelries that are that big or millimeter or centimeter size, but very, very, very tiny objects in the nanometer scale, where you could plate objects that are 10,000 times smaller than the width of the human hair to basically make technological devices, computer memories, processors. Um, that's the hypothesis. The hypothesis. We go to the lab to do the experiments, see whether it will actually work, and when it works, we publish the results. So we go from observations about electroplating, we do our research, and then we come up with a hypothesis about shrinking that method to a smaller scale. And then we go to the doing the experiments in the lab, and then we reach a new conclusion that maybe it's successful, or if it's not successful, we say that's why it's not been successful. Once we did this and this, and we think maybe we should have done an alternative approach or a new method to sort of do this work, and we expect that to give positive results later. So uh, this process of the scientific methods is what defines the character or the day-to-day work of a scientist. This cycle, this loop of this protocol of procedures is what we do, and to me that is science. Doing going through these processes is doing science, and doing something else is actually not exactly science.
Okay, so it's more for you about the, I keep hating to use the same words, but it's about the method as opposed to the field or the particular topic. Those don't define the science. It's how you approach it that defines the science.
I think so. Yeah, to me that's how it looks. But a general definition is science has to be systematic. So you study things systematically, rigorously, um, using observations and experiments to come up with conclusions. We call this induction. I don't want to go into too much details about induction and deduction, but um, science progresses naturally via inductive method because you use observations to reach conclusions, um, and that's what, and using the scientific method is the procedure or the protocol that you go through to do science.
Right. And so this particular series of videos is about theory and how theory sort of could be reintegrated into the humanities, especially into history. So, where do you find theory as sort of what does theory mean for you in that sort of scientific world, and how how does it kind of fit in with your definition or your conception of what a science is?
Mm. So back to the scientific method. So and we in the scientific method we try and do when we ask a question, we do our own research, see if somebody's answered this before or what's the background information about the subject, and then we come up with hypotheses. So the hypothesis is this and that. So let's say the hypothesis is that objects attract each other. That's the basics of gravity, the theory of gravity that Newton came up with. Um, um, the theory is when you study this hypothesis multiple times through rigorous experimentations, a lot of observations, and then you realize that this hypothesis is valid. It's actually standing against the test of all these experiments, and sometimes you call this a test of time, where people have actually went back and forth to it and try and falsify it, as how Karl Popper calls it, or tries to find problems with it. If it keeps on passing the tests, that's when we call this a theory. It's this theory is so some people actually take the word theory as a negative word, that um, it still needs confirmation, but actually a theory is something that a hypothesis that has been passing through a lot of tests over and over again, um, uh, to basically explain certain phenomena, explain certain behavior. So, for example, in the theory of gravity, we the idea is that objects attract each other based on their masses, their heaviness. Let's say, I don't want to call it weight because there's a difference, but the masses, and based on the separation between the objects. And then Newton came up with a theory so this is after many tests, we call this Newton's theory of gravity. Um, a theory could in science be sometimes described using an equation. So an equation is a model of a statement, let's say. So in okay, in English, objects attract each other based on their masses and the separation, but or the inverse of the square of the separation. And the equation would be F equals mass times some gravity divided by um, uh, the separation squared. So uh, it's a way of symbolizing using mathematics, using logic, this theory, this statements that we've mentioned in physics. That's what a theory is.
So it's really interesting that you brought in the idea of the equation being another way of expressing the idea, because when I try to explain theory to my students, albeit within a historiographical context, I usually say that the difference between a method or a perspective or some of these other things that they might use in history, the theory is exactly like you said, like an equation is given these inputs or these ingredients or this situation, this is what will come out on the other side, more or less. So it's a lot more difficult, I think, for historians to quantify the elements of their equation, but you do see sort of abstract representations of these ideas, I guess, into equations in sociology and geography without the expectation that you're actually going to stick numbers into that formula. But the general idea of if you have a surplus of food, it allows specialization of jobs in the economy because not everyone has to be a farmer. So as food production increase, the range of jobs increases. And you can kind of see how that's a formula without having the precise numbers necessarily. Although I suppose you probably could come up with numbers in that case. That's more of an economics equation, but the idea seems fairly similar. Now, my conception of theory is something that I gathered kind of ad hoc because I had a very broad liberal arts education and I have lots and lots of friends in the sciences and in the social sciences that we talk about these sort of things. But how was theory taught to you as a student in electrical engineering? How is it taught to you as part of your degree, part of your discipline?
Mm. So in science, let's say in physics, because that's what I'm involved in, or in engineering, a theory is an equation. But you're right, the theory is a much bigger definition for, and it manifests itself in different ways in different subjects. In science, which what makes science so successful is that it can quantify numbers. So quantify objects. It can quantify qualitative things. Let's say um, if let's say light is green light is a qualitative method of saying the light is green. Um, in physics, we quantify this as an electromagnetic wave with wavelength around 500 nanometer. So this is, and the fact that we could quantify things is what allows us to use mathematics. So to scientists, mathematics is a tools that we can use to represent our physical phenomena or physics, you, to come up with outputs later from the quantified objects that were quantified concepts that we developed. Um, so in the way we study it in school, and we learn about the theory. um, we tend to develop on the theory what we call models. So um, for example, let's say we learn about the theory of gravity. We know that objects attract each other based on their masses and inversely proportional to their separation. Um, so we use that to make models of, let's say, the solar system. Um, Unless you're a pure theorist that is developing new theories from the beginning, um, we use the theory to develop models of the, let's say, the solar system. So a model would be a system like the solar system, or would be something like the DNA, or it could be the cell, it could be something, an object or a system, and then we use this equation that drives the model, and some inputs, some initial parameters. So let's say the solar system that we're trying to model has got such and such number of planets, let's say 8 or 9, and then each planet has got that mass and that mass and that mass, and they're revolving around this star, which has got a huge mass, the sun. We give it initial parameters. These are the initial parameters: the masses, the locations where they are placed, and let's say the speed, how fast they're rotating or revolving around the sun. And then that model will give us conclusions. Sorry, will give us outputs. So the output would be the location of, let's say, Earth after 6 months would be have made half a revolution around the sun, or um, after 6 months, Mars would have revolved less than half of a revolution because it's kind of far away. So this distance, the fact that we have a theory, we can use it to model how far, let's say, planets revolve around the sun, um, of the solar system. And so we start with, so the model's got a theory. It starts with um, an input, and then it's got a theory, and it does some processing and comes up with an output. If you think about it as a calculator, your input would be 5 and 3, and the theory would be a multiplication, and the output would be 15. So sometimes you could, if it's so, and that's how we use theory. In science, or the way we taught about theory, we study the theory, and then we use it to make modeling of complicated systems. And we usually use computers these days because computers are very good at crunching numbers. You could give it all these numbers as inputs, and you could tell it to give us an output within a fraction of a second. Um, or sometimes it takes days of modeling, depends. Um, So that's how we taught to use theory in science, especially in engineering as well. Um, Using theory, we do the modeling using theory basically.
So it's more about a toolkit that you can draw from when you have certain questions or when you need to have a certain model. You say that this is sort of the theory that's most appropriate, and then you apply it to your specific data that you have in
Yeah,
any given case.
it could be it could be used to predict, for example, events in the future, or it could be along a time frame. So, as we said, it could be used to predict where the planet's going to be after 6 months, or it could be used to predict um, behavior in space, so in three-dimensional space. So this place is going to be there, in that location, and so on. So yeah, it's a model is a representation of, or you can think of it as a tool to understand phenomena better, without having to actually experience the phenomena, without having um, to experience what the solar system is going to be after 6 months. So yeah, you can
Great.
think of it as a tool, I think.